All right, so problem set 4. Everyone have your answers? All right, here we go, problem set 4. So the first one, please pay attention. I'm doing this for your own sake. Okay, so number 1 should be 0.0500 moles. Okay.
More significant figures.
Significant figures is a plus. Okay. Number 2 should be 2.41 times 10 to the 24.
Oh, yeah.
Okay. 3 should be 19.9 moles.
I think my calculator is right.
4
Oh,
should be 4.52 times 10 to the 23rd. Adam. Okay. 5 should be 2.41 times 10 to the 23rd molecules.
Molecules, that was Adam.
I think it's molecules. Is it atoms?
This is problem 5.
It asks
Yeah,
how
molecules.
many not.
Yeah. 6 should be 0.64 moles. 7 should be 800 grams.
Wait. 7?
7, yeah, 800 grams. If you put 798.5 grams, then you would be off on your sig figs. Be around at 800.
Did I calculate that wrong? I did. I didn't calculate.
Did you calculate it wrong? Okay, 8 should be 11.3 moles.
Wait, is there only one sig fig in there? Wait, so shouldn't there be a decimal here?
Number 9 should be 7.57 times 10 to the minus 3rd grams. 10 should be 230 grams.
What?
11 is 0.672 liters. 12 is 0.5 moles. 13 is 1.12 liters. 14 is 26.88 liters. Okay, how are we doing so far? Okay, now 15, some of these could get a little bit tricky because you need to make sure that you're recording the right or getting the right formula. Okay, so 15 should be 9.03 times 10 to the 22nd oxygen molecules. 16 is 12.62 grams. 17 is 11 liters into, this is the F2 by the way, and 18
What? Yeah.
is 4.65 grams of N2, and finally 19 is 3.69 times 10 to the 21. Woo! Woo!
Did it, sort of.
Did we do it?
Potentially.
Potentially.
Potentially accomplished.
All right, let's talk, shall we? Sir.
So why is, I thought isn't mole just 6.0 times 10 to the third? Like if you multiply.
Okay, so on sig figs, as I mentioned clear back in the first 0 unit at the beginning here, that when you're doing dimensional analysis of any kind, okay, the digits, okay, the number of significant digits in your original measurement that they're giving you in the paper, that's the number of significant figures that should be recorded in your answer. You should not use conversion factors to determine significant figures. So molar mass does not determine significant figures. Avogadro's number does not determine significant figures. If you did that, then anytime you use molar mass or Avogadro's number, then you would only have one significant digit every single time because of the 1 mole. The 1 mole would be the dictator, okay? But 1 mole is an exact number, okay? So it's not an actual measurement in this terms.
Why for like, if the mole isn't a measurement, so for example, for number 7.
It's not considered a measurement that we're doing.
Yes.
So for number 7, there should only be 1 sig fig. Because it's just 5. That's it, 5. 5. 1 sig fig.
Yeah, but I'm kind of confused about why you're using, because you said mole is a converted factor, right? The measurement is the atomic.
5 moles is what you're originally given.
If it says it in the problem, then that.
5 moles is what you're originally given. It is not a conversion factor. That is what you're given. I have 5 moles.
Should be 600.
So so you only have 1 significant figure. Okay, conversion factors are not going to affect significant figures here. Okay, it's a standard that AP has worked out so that it will bring in too many confusing answers. Okay. Yes, I can show you how I got 7. Do you understand significant figures when it comes to this stuff? Okay, so let me go through. Number 1 should only have 3 significant figures because of the 3, 0, and 1. That's right. So number 14 should have 2 significant figures. So really, yeah, this should be off. I'm sorry. This should be really a 7. And 13 should be 1. Yep. 12 should be 3. So what? That 0, 0. Yes. What? 11 should be 2. Yeah. It is. No, wait a minute. No, it's off 1.
Wait, so 1 is 3? What? 1 is 3, right?
So one has 3 significant figures. Usually AP is really good about kind of being flexible with 1 significant figure off in most of the problems.
11 is 6, 7 now?
Well, it's just because we rounded so that we got significant digits. Okay. Good. Okay. Now, yes. Yeah, so we have requests for 17 and for 7, okay?
I have 3, but I think my calculator might help.
3, you have 3 requests?
Yeah, on 3, no.
Oh, number 3, okay. So let's do this, okay? Let's start out with 3, since that's our first one we want, that's, closest to 1, right? And then we'll work from there. So we got 3 for sure, 7 and 17 that we want to look at. Is that correct? Okay, does everyone have the answers down? I'm about to raise them.
Yeah. Significant figures. Where's the key?
All right, 3. So what you have to remember in 3 is that you're trying to go from atoms to moles, right? So 1.20 times 10 to the 23rd atoms. Okay? Make sense so far? Yeah. Okay. And 10 over 1, right? There's our fraction.
It's under the 25th.
Right, and then we're going, 25th, thank you. And then we're going to go from atoms, so 6.02 times 10 to the 23rd atoms to 1 mole, right? And so I should just divide there.
Yeah, I divide and I get that.
You divide and you get that. Holy mackerel, that's not good. I know what your problem is. Your problem is parentheses. When you divide using that calculator, you're going to have to use parentheses when you're using exponential powers like this.
I see.
That's your problem.
Okay.
Parentheses. So we get what, 2? So 19.9.
19.9. There we go. That fixed it.
That fixed it, right?
Yeah.
So this is number 3. Not that anyone else had issues with that, but calculator issues do happen, and it's a good example why you really need to know how your calculator works, right? So I'm glad we're going over this because you learned something. Right?
Yeah.
Your calculator. Some of you that do not have a graphing calculator, but have a TI calculator, you'll probably be in the same boat. When you divide, you might have to use parentheses. Okay? Unless you have a EE button on your calculator. Do you have an EE on yours?
What the heck is it? What did you do? Oh, the two circuits here. So
You sort me right here.
if you do 1.2, yeah, that's what I used.
Okay.
E89. Bro, wait, that means 10 times 10 to the
Yeah, the EE button is the best thing that the TI came out with overall, I think.
With 1.2, number of particles in the observed volume.
Yeah, let's do 17. Nitrogen. Okay, remember. Please, this is important. Remember that the dirty 7 is going to get you. That's why I call them the dirty 7. And nitrogen is one of those. And some of you might have been caught with 15, possibly 16, although I give you up to you. 17, 18, and yeah, those are the ones. You've got to remember that oxygen does not exist in nature as O. When they mean oxygen gas, they're referring to O2. If they're referring to fluorine, it's F2. Nitrogen is N2, okay? Br2, chlorine, Cl2, okay? Be aware of the dirty 7. So 17, let's do this anyway. So 14, this is number 17. So we got 14 grams of N2, okay, over 1. All right, so that means that you have to double the molar mass, right? So the molar mass of nitrogen is what, 14.01? So that would be what, 28.02 grams to 1 mole of nitrogen. Okay, now we're talking about a volume of gas at STP. Okay, so 22.4 liters is equal to 1 mole at STP, right? Standard temperature and pressure. Standard temperature and pressure, which is 0 Celsius and 1 atmosphere. Good. Okay, so 1 mole to 22.4 liters of nitrogen on the top. Okay, good. We just want to make sure that we're good with this. So 14 divided by 28.02 times 22.4 leaves us with an answer of 11 liters of nitrogen.
I wanted to go for 7.
Yes, we'll get to 7. Thank you. Is everyone good with this? Understanding how to use STP volumes. Okay. Now again, this only works at STP. So if they're asking for a volume of gas and it's not at STP, can you use this relationship? No. Does everyone understand that? Okay, that will come important. Now, we will get into situations of volumes of gases at non-STP conditions in Unit 4. Okay, so that's down the road a little bit in quarter number 2. Okay. All right. For now, are we good? All right. Let's go to, I believe, 7.
No.
All right, 7. They're asking us to find the mass given 5 moles, right? So 5 moles of iron Fe3 iron oxide. Write that a little bit better. All right, so in order to go from moles to mass, you need the molar mass, right? Okay, so if I use the periodic table over here, I'm going to calculate my molar mass. So iron is 55.84 or 85, right? 2 decimal places. I have 2 of those. Okay, and then oxygen is 15.9999. So in other words, it's 16, right? So I'm going to add essentially 16 three times. And I should get 159.70.
What?
Did I do it wrong?
No, why is everybody saying like all those words?
What's,
That's correct. How's that wrong? Yeah, why is everybody saying words?
this is right, right?
Yeah.
I put it in my calculator, right? So then I just multiply that by 5. And to one significant figure, I suppose it would be what, 800?
Divided by 7.
800 grams of
So.
iron oxide.
Polonium. Oh my God.
Polonium. Is that where you messed up? On the molar mass?
Is this?
All right, do we want to go over any others? General question. For this problem set, I believe that's the only diatomic ones I have. That all of them are fair game. Any diatomic element is fair game on the test. The dirty 7 that we went over with. So in your notes, you should have it back earlier on. We talked about the 37. Yeah. Lesson 1 actually. I think we ended up talking.
I've got those ones right.
Wait.
I don't know, but it's really important. Yeah. All right. Let's go over the dirty 7 one more time, okay? For those that missed this for some reason. Okay. So the dirty 7, you look at the periodic table up here, starts at element number 7, where nitrogen is, okay? So nitrogen is element 7. From nitrogen to oxygen to fluorine, down to chlorine, bromine, and iodine, and even acetine, but we don't really use acetine much. We don't really count that often. So really, if you look at it, it makes a 7 in the periodic table, right? Starting at element 7. Okay, the only one that is not in that grouping is what? Hydrogen, okay? So with hydrogen, it makes 7. So 1, 2, 3, 4, 5, 6, 7. That's the dirty 7. They're all diatomic, meaning that you have H2, N2, O2, F2, Cl2, Br2, I2, and so forth, okay? Now acetine 85 is a diatomic element. It is At2. However, no one uses acetine because acetine is extremely radioactive and dangerous. Okay? So you don't find materials much with acetine in it. Okay? And it doesn't really, you don't find a lot of acetine in rocks and so forth.
Because it's kind of hard to.
Yeah, it is.
It's usually gone.
Well, it usually decays into lead. So, yeah. That's true. All right. Are we clear on the dirty 7, the diatomics? Yeah. All good now? Oh. We did. Oh. Okay. That was it. Gosh. All right, but you got it down? Okay. All right, what else? do we want to do with this problem set? Are we all good?
Yeah.
16.
60.
16. 60. Okay, number 16. Coming right up.
But we're not worrying about that.
All right. So,
I
16.
got
We're trying to find the mass of 200 times 10 to the 23rd molecules of F2. Okay? So we got to go from molecules to moles, and then moles to mass. Okay? So being the fact that it's F2, we know that there are 6.02 times 10 to the 23rd molecules of F2 in 1 mole of F2. Right? Correct?
Agreed.
And then we're going to go from moles of F2 to mass. Now remember that it is diatomic. So you have to consider that. So fluorine has a molar mass about 19 grams per mole, right? Everyone agree?
Yeah.
So if it has 19, 19 times 2 is what?
I wasn't answering, but I have a question.
Hold on, let's finish this up first. 30, 38, right?
No.
38. All right, you're close. All right, so my moles cancel, my molecules cancel, leaving you with grams. See how that's set up? Okay. And then from there, I can just calculate 2.00 times 10 to the 23rd divided by 6.02 times 10 to the 23rd times 38. And to 3 significant figures, 12.6 grams of fluorine. Okay? All right. All right. What is your question?
So, if you have F2, is that what do you refer to that as?
Fluorine?
It's just, so like, how does the question word it? Is it molecules of fluorine or?
Yeah, so some would consider F2 as a molecule, like H2O2. So a lot of times they'll use the term molecule for those.
Okay.
And it is in its normal, natural, elemental form, okay? We don't have isolated O's and F's and CLs in nature.
You don't really have an
okay?
atom of fluorine.
No, you just don't have a fluorine. You don't have what we call monoatomic fluorine that really exists in nature, okay? Diatomic fluorine is what occurs naturally in nature. Okay, does that make sense?
Yeah.
Okay, so when we're referring to these diatomic elements, we're just basically saying, hey, these are the natural forms of these elements in nature. This is how we're going to find them. You're not going to find O or F or Cl in nature, okay? Now, you can find them in the ion form. So let me clarify that. You can find them in the ion form. Like you can find F minus, O2 minus, or O2 2 minus, okay? Nitrogen in 3 minus, and so forth. So you can find those ions in nature by themselves, but not as a neutral atom. Okay? Okay. I want to be clear on that. Hopefully we would.
If you had it in like space in a vacuum, a single oxygen atom,
No.
what is?
No, I don't think you're gonna, as soon as, first of all, I mean, let's just say if you had only one oxygen atom in a vacuum and nothing else there, yes. Nothing else. I mean, nothing. I mean, a single oxygen, right? Okay. But if you have like even 2 or 3 or 4 atoms of oxygen in a vacuum of space, you're going to have O2.
Yeah, what if you had 3? Yeah, what if you had 3?
Yeah, then you're going to get ozone.
Wait.
What is ozone?
O3. It's O trace.
It's O trace. O3.
We'll trace that. Thank you
Yeah.
for the Spanish lesson.
O trace.
Yeah, ozone is
O
O3.
trace.
When does the living come across? Holy
What is the
mackerel.
smallest thing that is classified as living?
You just like opened up the biggest, largest discussion ever.
This isn't biology. I almost felt.
All right. In reality, a definition of science, we do not consider
Life to be useful.
elements or compounds as living things. Okay. Now, there are some debate on certain compounds like purines, or not purines,
Pyridine.
not pyrimidines, prions. Thank geez.
Prions?
Can't even like say anything. Prions.
I was close.
Now those are specific proteins that seem to have a mind of their own in replication, and that causes mad cow disease. Okay. However, most will still say no, not living. Okay. So when it comes to living, not until you really get to the virus where the debate really begins to open up. Okay, so the real question is, viruses, are they living or are they non-living? Okay, so where vast majority of scientists stand is that a single cell is considered the first living thing. Okay, so a bacteria, which are single cell organisms, they're living things. Okay, anything that has a single cellular structure is considered a living organism in scientific terms. In terms of viruses, there is an ongoing debate. Where do viruses fit into this? Because they're kind of on that, wow, 1 foot in as living and 1 foot out as non-living. Okay, so they're kind of this organism that is like dead and alive at the same time. So it's weird. Okay, so somewhere the virus is crossing that pathway of non-living to living. Okay, but as far as cells go, we consider them living. Now that's scientific terms. Now political terms, that's a whole nother ball game. Okay, I guess it depends on which political party you belong to determine what life is and what isn't. Okay, but science considers life living things at the cell level. Okay.
What's the part that makes it not?
No, that's 25 minutes.
How it reproduces. It cannot reproduce on its own. It has to have a host, a host organism to help to make it or allow it to be reproduced. Okay, and then as far as it being on its own, without the host, there's no growth in it. Okay, but then again, I mean, there's scientists that will debate the argument of viruses being alive, and I'm sort of on that line. I kind of feel that viruses do have a tendency to be considered living things.
What about?
But I will definitely say at least the cell level. Yes.
What about when, you know, the Heisenberg uncertainty principles, when you're observing something, it has a different behavior than if you're not observing it?
That's right.
Wouldn't that be, because it can change its behavior, would that be considered living?
So that Heisenberg uncertainty principle only really works in very small subatomic particles. Okay, you're too big. Okay, Heisenberg uncertainty principle does not apply to you. Yeah,
Yes, but the electrons behave differently when you look at them.
yeah, but we're talking
I don't
about
understand.
a very
I don't think I
different
have to, so I
situation.
don't.
Yeah, but
Okay.
how do they know that this is?
It sounds too complicated, so I'm gonna do my problem.
Guess what? After the test next week, that's where we're heading towards. Heisenberg uncertainty. Talk all about it.
Great. I'll do my.
Then you can get your headaches then. We won't get headaches.
How many milliliters are you
All right.
gonna make one?
Are we good? Can we move on from this? Okay.